Yeah, so thanks for, can everybody hear me all right? Does it, no? Let's turn something on. Oh, yeah, that one is on. Okay, let's try again. That's better? Sounds better, okay. Yeah, very happy to be here. I actually did my postdoc here in Edmonton, so it's always nice to be back. And so the topic I'm going to talk about today is sample-efficient reinforcement learning. And it's a topic that I've been interested in since I was a PhD student. This is about 10 years ago right now. And yeah, so in those 10 years, a lot of things happened. The whole deep learning revolution happened. And on the wings of that, reinforcement learning, DLRL, became a lot more popular as well. And it also had certain consequences for this, the research. So I want to say in the 90s and the 2000s, like a lot of methods and techniques were introduced that were ultimately really trying to get better sample efficiency. And when you think about that, it sort of makes sense because back then your representation was either a tabular representation or a linear representation. And in those settings, especially in the tabular, if you have a tabular representation, you have convergence guarantees. So you know if I give it just enough sample, I'm going to converge to the optimal policy. So under that setting, it makes sense that your main metric is how many samples do we need to get to that performance. Now, with the introduction of DLRL, let's call, say, 2015 the DQN Nature paper. To be clear, there were already neural networks combined with RL much earlier, but that was really sort of, the networks became a lot more deeper, and from that moment we could solve much bigger problems. So, but DLRL has the problem that there is a lot of instability, so you don't typically don't converge to your optimal performance. You converge, you get some performance, but it's you know, not guaranteed at all that it's the optimal performance. So since then, the focus sort of shifted towards the final performance, or what's the maximum or the best performance. So what's the best performance I can get on a particular game, for example. And so so for a short period of time, I want to say sample efficiency wasn't as important anymore as it used to be. And it's also because a lot of that research happened in games, and if you have a simulator, samples are cheap. But I want, it is a very important topic if you want to do RL in the real world. And what you see in, say, the last year, maybe year and a half, that there is renewed interest in sample efficiency, rightfully so. But now it sort of takes on a sort of different form, like in the era of DLRL. It's very different techniques. We think about it in a different way. So I'm going to talk about that as well a little bit at the end of this talk. But I'm going to start simple with a picture you've all seen in some shape or form, the basic model of RL. So we have an agent, we have an environment. The agent takes actions in the environment, and the environment responds with an update of its state and a reward. And we can describe the behavior of the agent as a function that maps states to actions. We call that the policy pi. And typically, the goal of the agent is to find among all set of possible policies the policy that results in the highest sum of rewards, or sometimes the discounted sum of rewards. So that's our basic problem. Now, so what does sample efficiency mean in this context? Like, how do you measure sample efficiency? Well, you can measure it in a number of different ways, but typically what you will get is sort of a curve like this. You have some performance. This could be your expected return, your average return, and that gets better and better when you see more samples. So one thing you could do, say, okay, I have a certain baseline performance, and I'm just going to measure like how many samples does it take me to get to this baseline performance. So that's one way to measure sample efficiency, and then obviously if you're more efficient, that's better. You need less samples. Like alternatively, what you could do is do it slightly different. You could say, okay, I'm just going to give my agent a certain budget of samples, some small number, and I'm just going to measure what's the area under the curve here, or the average performance. It's related to that. So that's just another way to measure sample efficiency. But like all the techniques I'm going to talk about, it's really, they apply to both. It's not, it's just different ways of measuring the sample efficiency. It's not fundamentally different. So coming back to why does sample efficiency matter? Why should you listen carefully to this talk? So it's actually something that is very important, as I mentioned before, if you want to do RL in the real world. And it's because of two things. The first thing is that in the real world, samples are expensive. So imagine, for example, working with robots, or even if you want to learn, if you're working with humans, so you want to learn, say, a dialog manager, how to come up with the proper responses to humans, then like that's super expensive samples, and so that's one reason to be sample efficient. But there is a second, potentially even more important reason, which is that the world isn't stationary, whereas like a lot of problems people focus on, they're sort of fixed, like an Atari game. The rules of the games don't change halfway while interacting. Well, in the real world, this is not the case. The real world changes continuously, and so learning quickly is key. So, and you could, like in certain circumstances, you could argue that it's even more important than what your final performance is going to be. Like after millions and millions of samples, it can be much more important to learn very quickly. And so I have as an example ad placement, which you can formulate as a reinforcement learning problem as well. So the problem there, you place a particular ad on a website, you want to maximize the click-through rate, and so you always want to show the most relevant ads. And well, that's very much a non-stationary problem. What is a relevant ad today is not a necessarily a relevant ad tomorrow. So in such a setting, you really want to learn very quickly, and it's way more important than sort of what performance you could have gotten if that, if the world was stationary. So these are two important reasons why sample efficient reinforcement learning is important. Like, we can do fun stuff in research, we can do fun stuff with games, but if you actually want to make things in the real world and have them be useful, this is a very important problem that we need to solve. And I say we need to solve it because we haven't solved it yet. We can do a couple of things. We can do, we can make methods that are more sample efficient than other methods, but there is still a very big open problem that needs to be solved. I'm going to come back to that later. So before I want to, for this talk, I want to give you sort of some tools, some ideas on different ways you can improve sample efficiency. So it's rather than being sort of very extensive in all the different methods that improve sample efficiency, I want to focus on, okay, what are the general techniques you can use to improve sample efficiency? So to talk about that clearly, I have to introduce a few formal definitions. I'm just going to keep it very light on definitions, so don't worry about that. So these are very basic things that you probably already know. So we have a Markov decision problem process. So we're going to formulate our RL problem as such. So we have S, the set of states. We have a set of actions A. We have a transition probability function P, which tells you what's the transition probability to a particular next state if I take an action from a particular state. We have the reward function. And finally, we have the discount factor, which tells an agent how it values immediate reward versus reward that come in the future. So, the return at time t is defined as you see over there. So it's the discounted sum of rewards from time step t onwards. And there is, I just see the definition of a policy is missing, so I'm just going to explain it in words. So policy is just I explained it on the first slide. It's a mapping from states to actions, or it could be a mapping from, if you have a deterministic policy, it's from states to actions. If you have a stochastic policy, it's from states action to from states to a distribution over a probability distribution over actions. And so related to a policy, you have two value functions. You have the state value function, which gives you the expected return conditioned on a state. So if I follow this policy, if I take my actions according to this policy, from this particular state onwards, what is going to be my future return? And you have the action value function, or the Q value function, which is the expected return conditioned on a state action pair. And so there are like two tasks that is good to know the name of. So if the evaluation task, which just simply means that I'm given a particular policy pi, and what I want to do is evaluate those two functions. So I want to approximate Q pi or V pi, but the more interesting problem is, and the one I'm mainly going to be talking about, is a control problem, is where you simply want to, for a particular given MDP, you want to learn what the optimal policy pi star is. And right, and so so how is pi star defined? So you can define a optimal Q value or an optimal action value function as such. So it maximizes the Q value function over the policy. And if you act greedily with respect to that policy, you're getting a pi star. So there is a certain, so this also sort of highlights a particular solution strategy, one that I'm going to be mainly focusing on during this talk, which is you just try to, or just, you try to find an estimate of Q star, and then once you have a good estimate, if you act greedily with respect to it, you have a optimal policy, or a close to optimal policy. So yeah, so that's the general. I'm going to try to explain all different techniques within this context, just to keep it consistent and simple. So this is our problem. Like in the general case, we're using function approximation, so you have some weight vector W, and you're trying to, from a sequence of samples, you're trying to find Q hat, which approximate Q star, the optimal Q value function. And so we're working in the RL setting, so all the agent can do is take actions. It can't just jump around in an environment. So from the sequence of samples, it has to find this estimate. That's our problem. And we're going to be using, our main learning technique is stochastic semi-gradient descent. And you see the update equation over there. So these are just three different forms of the same update like the linear is a special case of the nonlinear one. So it's just the stochastic gradient descent update, the above one. The linear is when you have just a linear function, and then it simplifies as such. And the tabular case simplifies even more, which is when you have a linear representation plus a one-hot feature factor as input, then you reduce to the tabular case. So, but yeah, they're all just particular forms of the stochastic gradient descent. So like if you wanted to, you could implement a tabular method using PyTorch or TensorFlow. It would be a lot of overhead, but it's just a special case. That's the thing to keep in mind. And so the semi in semi-gradient comes from the fact that your update target, UT, is typically not an unbiased, so it's treated as a constant when we write those update equations, but in practice it depends on W as well, because you bootstrap from other value estimates, and that's why like it's not completely stochastic gradient descent unless you have some special cases, such as the Monte Carlo update target where you don't bootstrap, but that's what the semi, where the semi and semi-gradient comes from. So here's just an example of the target. This is the Q learning update target. So you take the reward, the immediate reward, plus the maximum Q value of the next state. Okay, so now what are the different ways sample efficiency is affected if you consider this process? So this is all we have. What are the aspects that that affect your sample efficiency? There are basically 4. So you have the bias, the variance, your exploration strategy, and generalization. So what's your function approximator that you use? And yeah, they affect the sample efficiency in different ways. And I try to visualize that over here. So in each case, we're just trying to estimate a function, right? And so bias of your updates means you maybe get different samples for a particular value, for a particular state action pair, but all your samples are sort of off. So that obviously makes it harder if you want to learn that blue function here. If all your samples are off, that's a problem. That's going to cost you something. Variance is another problem where maybe on average your bias is low. So if you take the average over many samples, you're going to hit the right spot on the blue curve. But yeah, obviously if there is a lot of variance in your samples, that's also going to affect your sample efficiency. Exploration is another one because in reinforcement learning as opposed to supervised learning, your samples are not IID. The agent controls how the samples are generated. And obviously, if you want to have a good quality function, you should get samples sort of uniformly across your whole state space. So in this case, across the whole x-axis, you want to have samples. And if your samples are mainly focused in one area, which can happen if you have a bad policy, for example, that's a very big problem as well, because you're not going to get a good estimate of your Q star function, which really you need to be accurate across the whole range. So that's another problem. And then finally, generalization. So this just means that if I get a single sample, I'm not just affecting the value of that particular x value, but also the one that are close to it, according to some metric, and that can, that affects obviously sample efficiency as well. So these are, when we talk about sample efficiency, these are sort of the 4 categories that you can evaluate methods on in terms of how they affect the sample efficiency. Now, for this talk, I'm not going to talk about exploration because that's really, it's worth a whole separate talk. It's sort of and people don't typically see it as part of sample efficiency, but it really is. So, but it's a separate talk. It's a can of worms. I'm not going to touch it. I'm mainly going to talk about bias and variance, and at the end of the talk, I'm going to talk about generalization. And so, but first, I'm going to focus on bias and variance, and a lot of the methods that were developed in the 90s are really sort of in the tabular world where your representation is tabular. You can really interpret it as sort of different ways to deal with the bias and variance of your updates and trying to find ways to do it in a very sample efficient way. So I'm going to talk about that first. Yep.
Question from this slide. So what are the axes exactly? So one is the Q value and the other axis?
Yeah. So the way you can think about it is on the x-axis you have your state space, so your states are your state action pairs, and on the y-axis you have your Q star. Because if you go back, so this is the problem that we're trying to solve. We want to find Q star. We find an approximation of Q star. So the inputs of this function are your states, our state action pairs. So that's your x. Yeah, so the samples provide your update target, which is some estimate of your Q star for the same state. And it could be, so variance, I'm going to talk about it more, but variance could be due to environment stochasticity. If your reward is stochastic, your Q star tries to represents the expected sum of rewards, while what you're measuring are just single rewards, so there is some variance there. Yeah, and also I just want to mention, if you have any question, just raise your hand. Don't feel free to interrupt me. Yeah, there.
So the bias and variance are the bias and variance of the target from which you're bootstrapping, but not of your estimate, is it?
Sorry, say it again.
So the bias and variance in the plot are the variance and bias of the target that you're bootstrapping from.
Yep. Well, yeah. So what's the source of the variance you're talking about? Yeah. So I'm going to talk about that. Yes.
Sorry, is there a connection between the exploration one and the bias, in the sense that would the exploration be like a selection bias, sample selection bias?
So there are definitely sort of relations between these different topics, but like I try to separate them as much as I could. So in exploration, what I really mean is the way you you draw your samples from your whole state space. And whereas with bias, I mean, it's really about bias of the update target. So that's how that, so say you pick a particular state action pair, what's your update target going to be? Is it going to be in expectation right on point, or is it going to be some bias? So all of that hopefully gets clear when I talk. I try to first give a sort of an abstract idea of what we're going to talk about next. Hopefully it will get more clear in the next few slides. Any other questions at this point? Yes, in the back.
I just have one question on the exploration.
Yep.
You mentioned that suppose if you explore almost always, then you are still okay. That means you're always having IID, right?
Sorry, can you repeat it?
Always explore.
Yeah. Well, so if you say you have a policy that is 100% random, that picks action that doesn't mean yet that you get samples uniformly randomly, because your agent acts starts in a particular state and then has to follow a trajectory through that state. So it can like, if your environment is complex, it's still like a random policy will probably mean that the agent stays in approximately the same part of the state space. Yep.
You would basically have a thing because any other state you would reach you start off with a set of random initializations. You would sort of reach every other state, right?
Yeah, so the question is, we're dealing with a fully observable state space, and you have some policy that is very, takes random actions. So then, like, your next state is always going to be close to the one you're currently in. So that already means there is, you're not sort of drawing a random sample from your state space. And just by that fact alone, that can really mess with things. It means your samples are not IID. A lot of supervised learning is built on that assumption. We're using like deep neural networks built on that assumption. So, it's natural that issues are going to arise, and it's actually, it's a very hard problem to actually like think of the game. Well, think of a very hard problem where. You have to build some very complex tower, and only you get a +1 reward if you build that whole tower. Now, if you just have a random agent, the fact that it's ever gonna build, blocks on top of each other, that probability is just super low. So yeah, a random policy definitely, doesn't give you IID samples. So it's a hard problem. Okay, so Okay, so let's take a closer look at the bias variance in our updates. So here is the generic update rule based on stochastic gradient descent, but for the tabular case. And I'm just going to discuss the tabular case because all the, I can explain everything using the tabular case, so it's just a more simpler case. So this is our general update, and say we have the Q-learning update target, which is the reward plus gamma and the maximum of the Q value of the next state. So now if I had an ideal update target, so an update target with no bias and variance, then this would be my update target, which is simply Q star, which is equivalent to the expected discounted sum of rewards. So we can write these two forms a little bit more similar, so it's easier to see where the bias and variance comes in this update. So the Q-learning update I can rewrite as such. So instead of the max, I just take it just takes the action corresponding to the current policy, and the current policy is the greedy policy with respect to QT. And I can write our ideal update as follows. I can write it as well as a sort of a Q value in there. So now it's our so the immediate reward plus gamma times the action under the optimal policy and the optimal Q value function for that. So now we have two very similar equations, and we can immediately point out. Immediately point out where the bias and variance occurs. So if you look at these two, Qt and pi t, so the updates equations are similar except for these two differences. So instead of Q star, the optimal Q value function, we don't know that one yet. I use some approximation which introduces bias. And instead of taking my pi star, my optimal policy, I also don't know that yet. So we just use our current policy. That's another source of bias. So there are these two sources of biases. One due to just simply the fact that you're bootstrapping and you don't know Q star, but you're bootstrapping from some estimated value. That introduces bias. And the other one is due to the fact that you don't know the optimal policy yet, but you generate your samples according to your current policy, which is just some estimated policy. So two different sources of bias. We need different techniques to deal with them. Finally, the variance comes in over here because the ideal case, if you want to have an update target without bias, without variance, we're talking about the expectation. Obviously, we don't have that in practice, so that's the source of your variance. Well, you might wonder, like how do we deal with these two sources? Because obviously, if you have a bias, like how in the first place can we overcome that bias and that variance? So I'm first going to discuss the variance case, which is the easy case. So here again, you have your general update rule. Now I've rewritten in the second equation. I've just rewritten it slightly to get even more clear what that update is doing. So what you're doing is you're just taking a weighted average between your current estimate, QT, and your update target. So if you have a small step size, a small alpha, it means that you're putting a lot of weight on your current estimate. Whereas if you have a high value, you're putting a lot of weight on your update target. And so by setting your step size, you control your averaging. So if you have a small step size, you do more averaging at the cost of an increased sample complexity. Because now, like each individual update, if you have a small step size, each individual update has less effect. So it's going to cost you more, but you do more averaging. And that's, you need averaging to deal with variance. And if you have a large step size, you have less averaging, but higher, better sample complexity. Let's see, did I write that right? Small, more averaging, increased sample complexity. So it's small alpha, worse sample complexity, large alpha, better sample complexity. I think I mixed it up here. So what does it mean in practice? So you always want to set your step size as high as possible because that's going to give you better sample complexity. However, you can't set it too high because if there is variance in your update target, for example, if there is a lot of stochasticity in the environment, then you have to set it low, otherwise you end up with very bad value estimates. So there is some trade-off, and so there are, if you talk about methods to improve sample complexity that are based on this, you could think of methods that try to, from data, learn what the right step size is. That would be one way, rather than sort of picking a step size in advance. You try to learn what your best step size is based on the stochasticity you encounter in the environment. So that is one way to where you can exploit this to get a better method. Another way, another thing you could do is, rather than having sort of a single step size, maybe you have a task where maybe in parts of the task environment is very deterministic, but then in a few places it's very stochastic. So, you know, if you use a state-dependent step size, you can really exploit that type of behavior, that type of task properties. But like in general, like many of the techniques, so there's a few techniques that allow you improve sample complexity based on variance, but many of them are based on the bias, so that's the one I'm going to talk about next. So here we have our Q-learning update target again. We have these two terms that introduce bias, and so how can we deal with that in the first place? Like, if we have biased updates and we want to have an unbiased estimates, how can we solve that? And well, the short answer is by doing policy iteration. What that basically means, so there's a very general procedure for finding your optimal policy, which is you start with some random policy, pi, then you do evaluation, so you determine phi pi or q pi, so until you have, so you have that value function now, and then you do, you take the greedy policy with respect to that, and then you get a better policy. So there is this loop going on where you continuously try to improve your estimate of the value function of your current policy, and at the same time try to improve your current policy by taking a greedy step. And so by looping like that, you converge to both the optimal Q value function or V value function and your optimal policy. So so what does that mean for sample efficiency? So the short answer how to deal with bias is that every update you perform in expectation reduces the bias a little bit. So if you do enough of those updates, then the bias gets smaller and smaller until you converge to the right value. So now the way it improves so there is a number of different techniques that you can use to improve sample efficiency. So one is to, first of all, you can use update targets which have less bias. So, and we're going to talk about that. Those are multi-step updates. Another thing you can do is to use samples more than once. Experience replay is an example of that. And a third way is to play with the order in which you perform your updates, which is prioritized updates. So you try to perform those updates that have the largest effect. So it's really a way to smartly allocate your computational resources to only do those updates that have the largest effect. So those are just three different examples of different techniques that all try to improve sample efficiency by focusing on the bias. Any questions at this point? All right. So I'm going to look a little bit more now at the multi-step updates. So why would multi-step updates improve your bias? Well, so at the top I have again the Q-learning update. This is sometimes called a one-step update target. Now I can extend that update target by, instead of only looking at the immediate reward, looking at the combination of the immediate next two rewards, and then bootstrapping from the value that comes after that. And you have less bias in this case because you're now, well, first of all, introducing more real reward, but also, if you look at the discount factor, in the first one, you're discounting by gamma, the value. In the second one, you're discounting by gamma squared. So the effect of your value estimate is just smaller, the overall effect is smaller on your update target. And so you can go further, like follow this idea further to get an n-step update target, and in the limit, where you say, okay, I'm only going to use my rewards. You have the Monte Carlo update, which uses all the rewards until the end of an episode, and then you don't bootstrap at all anymore. So, like with respect to, so one source of bias is completely removed in that case. Of course, you still have the fact that your policy that you're using to gather those rewards, it's not your optimal policy yet, which is also a bias, but at least bias with respect to not using Q star to bootstrap from, that's removed. So you might think, okay, let's just always go with Monte Carlo, clearly the best, lowest bias. Unfortunately, that's not the case because there's this other issue of the variance, which is also affected by your update target. And in fact, the variance increases if you roll out, if you take longer update targets. And so so while the bias becomes less, the variance increases. So there is a trade-off, and the trade-off depends on your task, because if a task is very stochastic, that variance is going to increase more. And if the task is very deterministic, you might be able to use longer, like more multi-step, that can pay off. So it's really, so there is a trade-off, a bias variance trade-off to consider here. Now, so these are what are sometimes called simple updates. You can also construct combinations, weighted combinations of them. For example, let's take 0.3 times a two-step update target plus 0.7 times a five-step update target. That's also a valid update target in the sense that you're still going to converge to the right value in the end. Now there is one particular complex update target that is very popular, which is the lambda return, which takes a weighted average of all possible n-step returns, where lambda is a hyperparameter that controls like how much weight you put on your early, on sort of the smaller n-step returns, so n-steps with values 1 or 2 or 3 versus the ones that are a bit longer. And so the nice thing is now you have this hyperparameter between 0 and 1, and if you set it to 0, you get the one step, it reduces to the one-step Q-learning update, whereas if you set it to 1, it reduces to the Monte Carlo update. So by playing with that hyperparameter, so if you want to tune your bias variance, you can just play with your lambda value between 0 and 1 and sort of tune it such that you get the best performance. Now this is an example from the book I took just to illustrate this multi-step performance, and that that's a trade-off. So there's a couple of things to get from this graph. So the different lines correspond with different n steps. So the red one is n is 1, so that's a very short update target. And it slowly increases, so the green one is 2, the blue one is 4. And so what is measured is the average error over 90 states. And so the example is, so it's a random walk example, but then a little bit longer here. So this one has 5 states, the one from the figure has 19 states. And you're measuring early performance. So that's, like I explained in the beginning, another way to measure sample efficiency is you give it some fixed budget, in this case 10 episodes, and you see what's the average performance. So So what you can see here is a couple of interesting things. So first of all, if you look at the optimal, so the x-axis is the step size, and we talked about it before. The step size controls your variance, so you have to set it at the right value to deal with your variance. Now what you can see is that for the higher values of n, which have more variance, your optimal step size gets reduced. So that sort of negatively affects your performance. And yeah, and you also see that the optimal performance is not at n equals 1, it's also not at a really high end, it's somewhere in between. So that's, that's sort of a typical, if you would do an experiment like this, what you will see, that it's n is 1 is not the best, a really large one is not the best, so there's really this trade-off between bias and variance. Now, there is one more thing, sort of a refinement I want to talk about, just because it's, you'll probably get to hear it more. So now, there is an additional disadvantage of n-step returns, which is that there is a delay in when you perform your updates. For example, let's take the Monte Carlo update target as an example, which reduces rewards until the end of an episode. So if I use this update target, I have to wait until until the end of the episode before I can update any state values, which is, if you compare it with a one-step update target, obviously, in a one-step update target, you always, at every time step, you immediately update the state that you previously saw, and you can already use that. So you're improving your policy during while you're interacting with the environment, and so in some cases that can really, help. If your episodes are really long, it might pay off to improve during your episode rather than to wait till the end of an episode and perform your updates then. So there is actually a technique you can use to also get that same benefit for n-step returns. And this is what I mean with an online implementation. So the online implementation in this case refers to the fact that you update a state immediately after you observed it. So you're in a state, you take an action, and then you immediately perform the Q value of that last state or state action pair. And let's take as example the case that ultimately we would like to update with the Monte Carlo return, so low bias. So if you start, what you see here is a state sequence starting at state S0. You just have 5 states until you enter a terminal state. So now at state S1, I can already update S0, but I can only update it with a one-step update target, a one-step return, because that's all the information I have right now. So let's say, so the red line represents the time that we're at. Time goes from left to right. So at this point, I can already do an update. I can't do a Monte Carlo update, but I can do a one-step update. Now, if I go one time step further, I'm in state S2. What I can do now is I can, I could just update S1 right now. But what I also can do is I can forget the update I've done of S0, and I can redo that update, but now instead of a one-step update target, I use a two-step update target. So I'm doing now first, so starting from my, I undo the update I just did. I redo the update with a two-step update target, and then I do an update of S1, which is a one-step update target, because again, that's all I have. And so you can continue like that. So you redo all your updates. You start with your initial Q value, redo all your updates at each time step, until at the end, you've now done a Monte Carlo update for every state. So at the end of the episode, I'm again at the same point that I wanted to be at. I want to do a Monte Carlo update of all the states, but I've now done it in an online way so that I can already keep improving my policy during the episode. And now, the disadvantage of this approach is that's a very expensive technique, computationally expensive technique. So especially if you have longer episodes, because you need to first of all store all your states, store all your update targets, store all your samples, and then redo all these updates. So it's very expensive. However, in one particular case, you can do it very efficiently, which is if you use the lambda return as multi-step update target. And that's exactly what eligibility traces do. So this is a very popular algorithm, Sarsa lambda, Q-learning lambda, so anything with a lambda. So it's basically an efficient implementation of the online forward view with the lambda return as update target. And this is something I did research on myself. So the traditional methods, say Sarsa lambda or TD lambda, that sort of approximates that implementation, so that approximates that technique I just showed. But if there's true online Sarsa lambda, you actually exactly implement that technique. And if you exactly implement it, you actually get much better results. So yeah, so that is a way to understand eligibility traces. It's just a way of doing multi-step updates to get the best trade-off between bias and variance, plus not having to suffer from those delayed updates because you're doing this weird thing where you redo updates at every time step, which normally would be very expensive, but just, the mod just works out that in a linear case, if you use a linear function approximation, you can do it very efficiently. In the nonlinear case, you can't do that, unfortunately. So there you have to refer back to some approximation. Okay, so that covers the multi-step updates section. Yeah, question.
Could you give us an indication why the true online setup lambda is better than the traditional assessment lambda? Is that because it's online method compared to the offline method?
So the question is, why does true online Sarsa lambda perform better than Sarsa lambda, right? What's the core? So it's really it doesn't really have to do with offline with this difference, because even Sarsa lambda tries to implement the online tries to implement this idea. However, it does it in a way that extra errors are introduced. And like the reason is, like, this whole viewpoint was when Sarsa lambda was not how Sarsa lambda was developed. Like, different intuitions were used to develop Sarsa lambda, and it was a good algorithm. Like this one only very recently, like this interpretation was recently like I worked on that during my postdoc, so it's recent work. And from that viewpoint, it's actually like this approach is a good approach, but from this viewpoint as well, if you interpret Sarsa lambda in this viewpoint, then it does something like that, but it introduces additional errors. And that's why if you implement it exactly, and it just meant you have to, well, your eligibility traces should have a slightly different form, then you get, yeah, it just work better in the end because you really implement this viewpoint exactly. Yes?
Can you tell us about the problems that we face when we use eligibility traces in nonlinear function approximations?
Sorry, say it again?
The problems that we face when we use eligibility traces in nonlinear function approximations.
Right. So why can't we do this in nonlinear function approximation? Well, the simple answer is, like we can implement this view, which is called the forward view. This is a very general viewpoint. We can implement it in all, like, tabular, linear, nonlinear. So we can implement this, but this is very expensive. So this is not how you want to implement it. And in a sense, we just got lucky in the linear case that, you write it out, you get more and more mod, and all of a sudden things fall apart, and like you can cross things out, and you end up with this really compact, small update. This doesn't happen in a nonlinear case, and the reason it doesn't happen ultimately is that in the nonlinear case, your gradient is depends on your weights as well. Like in the linear case, sort of if you take the gradient, you just have this feature vector, which is independent of the weights, and that particular property is what we needed for the mod to work out nicely. And when you introduce nonlinear function approximation, that condition doesn't hold anymore. And so this property that you used in the proof to show this equivalence doesn't hold anymore. So, so the good news is you can still do things very close to this that are still like formally nice. Like you're not introducing errors, you're just having a slightly different viewpoint that is still solid. And so I have a paper on that actually that exactly tries to do that, and it's sort of, trying to remember the name, it's efficient multi-step updates for nonlinear function approximation, something like that. Yeah, but it gets many of the same benefits, but it doesn't use eligibility traces. Yes?
So if true online TD is doing Monte Carlo returns eventually, wouldn't it have variance?
Sorry, what's the last part?
If you're doing Monte Carlo
Yeah.
updates eventually with traces,
Yeah.
why doesn't it have high variance like Monte Carlo?
Well, so that's a very good question. So the reason is because this works with the Monte Carlo update target, which is what you get when you use the lambda return with lambda equals to 1. That is like eligibility traces hold for any lambda. Now, in this particular example, I just used because it's easy to visualize. So in this case also, the variance would be high, so it probably wouldn't be a good choice. But so the nice thing about the lambda return is that you can set lambda at any value and get one step or Monte Carlo. So yeah, this is just for visual, easy presentation, but it's probably not what you want to do in practice. What's going to give the best performance in practice? Okay, so let's have a look at experience replay. So experience replay is another way to deal with bias, and in particular you're trading some resources for better sample efficiency, because what you're doing is you're storing your observed samples, and then using those samples, you draw samples from this buffer, and you perform additional update based on these samples. So you need some extra memory because you need to store them, and you need some extra computation because you need to perform additional updates. But typically that's a very favorable trade-off. Like in most cases, I would very gladly trade some extra computation for sample efficiency. Now, in the deep learning setting, that all gets a little bit murky. We're going to talk about that, but sort of in traditionally, sample efficiency is way more, like samples are way more expensive than computation. So that's a very good thing. It's a very good trade-off if you can trade computation for better sample efficiency, and that's what experience replay does. And so what are the variations here of this idea of you can play with the buffer size. You can only keep the latest X samples, or you can store them all if you want. You can play, and the way you draw samples from it, that's another big factor in the different variations of this. So you can, in the most simple case, you draw uniformly at random, but you can also draw in sequence. So the original paper just stored like 10 samples or 20 samples and just did from first to last. And you can try to do something more clever and prioritize those samples that you expect will have the largest impact on your will have the largest impact on your value. Prioritized experience replay is one of them. Now, I just want to mention that like experience replay wasn't used that much in traditional RL, like tabular or linear function approximation. It became all of a sudden very important again in deep RL because it was used not for these reasons, but it was used to deal with the fact that you don't have IID samples, and we use now these techniques that very much rely on that. So then in that context, experience replay was just a way, if you just store lots of samples and then draw at random, it's sort of a little bit IID perhaps. So it became an essential technique, definitely during the early, papers, became an essential technique to make these DLRL methods work. But originally it was not developed for any of those. It was really a way to improve sample efficiency. So now if you go to the extreme of this, say, okay, you have as much computation as you want. I just want to optimize my sample efficiency. What can you do then? Well, first of all, I would just store all samples. So have my buffer size just grow with every sample I see and store all samples. And then at every time step, you could just draw many samples, perform many updates. But obviously, like if that's what you want to do, if sort of your computation, like if you want to improve at all costs your sample efficiency, then there are better methods, especially if you're dealing. Yes, question. So does this technique depend on how you if you use just a fixed step size? So yes, it works. You typically would use a fixed step size, or so it works. Like if your step size is small enough to deal with the variance. You can just use this technique to do many updates, and you will improve your sample efficiency.
And what would your conclusion be? Let's say if you use a step size equal to the number of times you've seen that particular state in action pair, because then in that sense your alpha just keeps changing depending on how many times you see the transition. Would that lead to like any performance benefits in terms of sample complexity?
So you're saying like, what if you play with your step size not to have it fixed, but have it using some count? And so that's a very good segue to my next slide, because so like if really resources are no problem and you want to just get your sample efficiency up, you wouldn't do it as I just described. You wouldn't store all your samples, use some small fixed step size. You would do something smarter, and that's when you get to model-based learning. And so I'm just going to explain it first from the tabular viewpoint again, in which case it's very simple. So what you see here again, I've shown those equations before. You have the general SDD update rule, and then you have two update targets. We have the Q-learning update target, and you have the ideal update target. Now, I'm going to rewrite again the ideal one slightly, so the comparison becomes simpler, because, we can rewrite the ideal one as such. So instead of that, so we're interested in the expectation over sum of rewards, but I could replace that. It's mathematically equivalent by taking the reward function plus gamma and then a sum over your probability distribution, and then taking the max over there. So these two things are equivalent. So another approach to approximate that ideal one is, well, what if I try to estimate my reward function and my transition probability function? Then I can directly construct that and reduce, at least reduce my variance that way. So this is what a model-based update does. So now I have some estimate r hat t, which is my estimate of my reward function. I have an estimate p hat t, which is an estimate of the transition function. And now, so again, that's some bias is introduced, but it's a very good way to deal with the variance, because in this case, sort of It's very similar to experience replay, but it does it in a more sample efficient way. That's one way to look at it. And because you average over, so you keep an estimate of all your rewards, your step size can just be 1 in this case. So your update reduces to this update here, and it's a very effective update in the tabular case. Now, in the linear case, you can sort of extend similar this as well, and it sort of still works there. Nonlinear, that's a whole different beast again, and none of this transfers over well, and it's still, it's still an open problem. People have tried, have a little bit of success, but like it's nothing compared to the difference between model-free and model-based in the tabular world. So it shows that there is still a lot to gain if you can do this in the deep learning setting, in a DLRL setting. So now I alluded already to it a little bit that this is very similar to experience replay in a sense that you're storing your samples and you use them for additional update. So I just want to point out a particular paper that I wrote a couple of years ago, which is here I showed exactly that. So I have 2 algorithms. The details, I'm not going to explain them exactly, but I have one algorithm that performs updates with TD0 updates, so the most basic sample-based update you can think of. On the right-hand side, I have a model-based update of a linear model, and what I showed in that paper is that these 2 algorithms, we have a model-free algorithm, we have a model-based algorithm. So a model-free that uses experience replay, we have a model-based algorithm. Like these methods are exactly equivalent in the sense, in terms of the values they compute. Like at every time set, they compute exactly the same values. So that shows a little bit more about like the relation between experience replay, model-based learning. Both of them are just sort of techniques to be smart about your bias and try to trade in computational efficiency for sample efficiency to deal with bias variance. Okay, finally, I want to mention Dyna from Rich, and this is sort of another way to way to view the relation between model-free and model-based learning. So in this particular case, it does a little bit of both. So it uses experience both to perform direct model-free updates as well as to update a model, and which is then used to for simulated experience. So you generate samples. So it's different than what I just showed, where you really you try to directly estimate your 2 functions, your reward function, transition function. Here you have a simulation model. So you draw samples from that and feed that to the agents as well to perform additional updates. So that's very much like it's another way to try to trade off computational efficiency for sample efficiency. Okay, so I have about 12 minutes left, which is good because I have only a few more slides left. So now we get to my to the talk outline again. Still not going to talk about exploration, but we now had part 1. So now I want to talk a little bit about generalization. And because obviously, like with generalization, especially if you talk about deep neural networks as a representation, since if you effectively can exploit them, can use them, you can solve much bigger problems that you couldn't solve before, that were simply way too big when you talk, well, definitely for tabular methods. So in a sense, generalization allows us to solve now much bigger problems than we could ever before, like these strong function approximators. But yeah, they come with a lot of instability, and they also, in terms of sample efficiency, they are, they're still far off if you compare that for human sample efficiency, for example. And so I just want to show one particular graph. So this is from the Rainbow paper, combining, so it's a DeepMind paper, So what is shown here is on the x-axis is the million of frames, so the number of samples. On the y-axis, it's the human normalized score. So you see percentages. At 100%, you're at human performance. And so, well, so the maximum, and rainbow, that graph at the top, that's clearly outperforming all other methods, not just in final performance, so it gets close to 200%. And to be clear, so this is averaged over all the Atari games, or 60 Atari games. And so, and it looks like super sample efficient. It's much more sample efficient as well than the existing method. However, if you would compare this to a human, then like obviously in terms of final performance, they're doing much better than a human. But if you look at the sample complexity, then they're really taking a very, very long time. So here I just put some numbers. So if you look at at what point, so the full training period is 200 million frames, which would correspond roughly with 370 human play days. And it's per game. So if you play 60 games, the agent got like 370 games, 370 days for each day, for each game. So it's a very long training period. I think we can all agree with that. Now, if you now look at Rainbow, the most efficient one, and we look at how long does it take to get to that 100%, to the human performance, then we're at 15 million frames, which is a lot less than 200 million, but it's still about 27 human play days. And so that's still a significant amount because it's play days per game again. And so, and they compared against a human, and this is not sort of the best human, that can, you know, it's not the optimal human in any sense. It's just some guy they you know, took up the street and had them put him in front of the computer and play each game for some time before they test his performance. Now, I don't know exactly how long that person got to train on each of these games, but I can assure you it's not 27 days per game. It will be much more likely in the order of maybe an hour. He played, and that's still a lot if you play because you have to play many games. So people really like to use these results to show, okay, we're doing so much better than humans, but that's really only one aspect. That's really in terms of sort of the final performance, in terms of how quickly humans can learn. Humans are way, way better when it comes to sample efficiency. And I just want to show you one other example of that, an experiment we did ourselves. So this is basically the most simple game we could think of. It's just a block that has to jump over another block. So we had a training set where we had this obstacle. We placed it in a number of different locations. And we had an agent train, we draw at random from the training set, and it learned to perfectly train to perform this task, as you can see over here. But then if you use a test set, if you give it a task where we move that object, that obstacle just slightly compared to what it has been trained on, now it's all of a sudden fails. Now, and that is an issue, like if you want to use something like this in practice. So for humans, this would not be a hard task. They would very quickly figure out from 3 examples or from 10 examples very quickly what the goal of the task is, which is, okay, you have to jump over this block, and very quickly it can then, you know, any obstacle location I give it to him, it still understands, okay, it's the same game, I just have to jump over this block, and it would be able to generalize. However, our algorithms cannot do that. And well, if you think about it a little bit more, then it's not that strange that our algorithms cannot do it, because our current algorithms are developed under the assumption that, you know, they learned fully from scratch and they have no prior information. Now, let's just say I give you one single example where it learns how to jump over a block. And now I give you a different example where the block is moved a little bit. So there is no way for the agent to know if it doesn't have any priors, if it learns from scratch fully. There's no way for that agent to know what it should do now. It just knows, okay, if I perform this particular behavior, it's okay, I get a good reward. But is it because should I jump at that particular location, or is it related to the block? Should I jump? Like, there is no way for it to know without prior information what it should do here. And these are just two examples. Like, if it has really no prior at all, there are like a million different other ways it could generalize. So when we say like our algorithm doesn't generalize well, what it really means is it doesn't generalize how a human would generalize. So that's implicitly we assume, okay, the way we generalize, that's the correct way of generalization. But it's really like, from a mathematical perspective, if it doesn't have any priors, if it makes no assumption, all these possible ways to generalize, they're equally probable. So there is no way we can like, it's a ill-posed problem. We can't generalize without priors. We can't get that strong generalization that we want. So, you know, to compete with humans on sample efficiency, we have to look beyond single task. And we have to do things like this: multitask learning, meta learning, transfer learning, continuous learning. And so that's the new sample efficiency research. And that's what I've been sort of mentioning about the last year and a half. Like we have focus on that now as well, other groups as well. But so this is how sample efficiency becomes important again, because yeah, we need it for the real world. But it has this different, it's a very different shape now than some of the earlier stuff, which was about bias and variances. But it's, yeah, it's very exciting. And I want to end with a quote from Charles Darwin to further motivate this direction. So what he says, it's not the strongest of the species that survives, nor the most intelligent, but the one most responsive to change. So that's the end of the talk. Thank you very much. We have 3.5 minutes for questions. Yes?
So regarding the part about generalization, especially when we are using observations of high-dimensional space, how much of the generalization problem comes from the representation that the inference network is learning?
So how important is the representation when it comes to generalization?
Because there are like, rather than methods that we apply in reinforcement learning, there are approaches from representation learning that can help us to learn invariant representation.
Right. Yeah, so in short, I think the representation is super important because that one example of the jumping block task, it's not that there doesn't exist a representation that can solve the task, because we can construct certain representations for which we get that type of generalization. Like if you would have taken, for example, the relative distance between the obstacle and the object, then it can solve this task well. So there exists representation, so clearly one certain representation generalize way better than others. In that simple example, we can reason about what that representation would look like. In the general case, that's a much harder problem. Yeah, I think representation learning research is very important in trying to become good at generalization. It's one path towards achieving that. Yeah, in the top?
You mentioned that we can get different updates by using different values of n for the multistep days. Can we also get like increasing number of updates by plugging in different policies, say like the SARSA or the Korean updates?
Yeah. Short answer, yes. Like there are many different variations of update targets you could use to try to, you know, get some benefits in the bias variance setting. So I've only showed, sort of to keep it simple, I've only showed Q-learning-based variations. Yeah, the one-step, multi-step is a very important general thing that you can use there. But yeah, there are, you know, there's off policy, on policy. There are definitely, the zoo is a lot larger than I can cover in this talk. So I kept it sort of very limited. But yeah, I mean, definitely. Yes.
Speaking of experience replay, I can obviously it's apparent that it addresses sample efficiency, but I cannot quite see how it addresses the bias problem. Does it help through like solving the bias problem, or we just get the chance to improve the data more?
Well, like the general approach to solve the bias problem is do many updates because each update reduces the bias a little bit. So a different way to look at it is that you want to, like, if you have some state space, all your states are, the value of one state influences the value of a state in a very different part of the state space. So in a sense, if there's an update of a value here, that information needs to propagate all the way to states far away. And a way to do that is just to do many updates. So if you do experience replay and I do many updates, that information gets propagated throughout your whole state space. And because that's really like underlying, if you have a stochastic environment, the value of one individual state depends on the value of all other states. So that's why, I need to do all these updates. And with experience replay, it's just, or you can play with the order. Like every update you do potentially reduces the bias a little bit. Yes?
I wonder what are your thoughts on how we can improve our current research on the model-based learning?
Sorry, on what?
Like, I wonder what are your thoughts on how to improve the model-based learning?
You mean in the nonlinear setting? Like I think there's no easy answer there. I think none of the techniques we've developed so far, which were all for the tabular case, will transfer over to the nonlinear case. Like I think we have to, from scratch, rethink again what it means to do model-based learning, because it's such a different setting from, like, in general, like a lot of techniques, because we're like a lot of algorithms and techniques were developed first for the tabular case, and then they, you had to show that they work in linear function approximation as well, and that sort of mostly works well. But then when DLRL came around, people still use those same intuitions they had from the tabular world and try to apply it in a DLRL setting. I think that's not gonna work anymore, because it's such a different setting. If you consider sort of a small maze task with maybe 100 different states, and you develop a method based on your ideas and intuition about that, and now you go to the real world where the whole idea of a task, what does it even mean? Like, it's super non-stationary. It's such a different beast than sort of that small little thing, though there's no reason to believe that what you learn from, or what you developed on that small task is going to translate over to that super hard problem. So I think like some techniques transfer over well, but like a lot of sort of those specialized techniques like model-based learning, that's just not going to work anymore. I don't, for model-based learning in particular, I don't see how we can really successfully transfer it over. In particular, like, so one, to give a more concrete example, so in the tabular world, what makes a lot of sense is to have a one-step model. Because the Markov property holds, so if you have a one-step model which just predicts what is your next state, it makes a lot of sense, and you can exploit it because the Markov property holds. In the real world, that's not necessarily the case anymore. So what you get to see there is that people still try to use those same ideas, so they try to use one-step models, but then they get this compounding error problem, and then they try to come up with techniques to deal with that compounding error. I think that's the wrong approach. I think fundamentally, don't think about one-step models. That was something from the tabular world. There's no reason why it should work in this super complex problem. So rather than trying to use these old techniques and then come up with things on top of it to now have it work in the DLRL setting, I think that's only going to get you so far. And in particular, our model-based learning, that's not going. I don't see how that really is going to work. We really have to rethink that.
And if we're going to kind of